How's it going, Bohan?
I'm good. How are you, sir? Can you hear me?
Uh-huh.
Good, good. Just fix my mic.
Yeah, sounds like you did. That's good. I signed in a little early. I'm your syllabus, I decided to change some stuff on the course, so I'm rejiggering it and plan on putting it up tonight or tomorrow. I gotta let everybody know that, but that's what I've been working on.
Nice. Sounds great. I think the class about started. I don't know where's everyone else at.
I know, I'm surprised they haven't started coming in yet, but
Yeah.
here we are.
Oh, sir,
uh,
I do have a question about our online exam. So
yes.
since we take like a whatever the lockdown browser the exam, so
Mhm.
I don't know the time. Is that had to be like a specific time to take it, or it just like give you a couple days?
Gotcha. So yeah, with this class, this is online. I'm going to have a midterm and a final. And what I'll do is I generally want everybody to take it at the same time,
Mhm.
or I have to make multiple versions. So it all depends on that. I'll know more maybe in a couple weeks
Uh-huh.
exactly what my plan
Okay.
is. So, uh,
Okay, I just want to make sure if that's like you had to be that specific hours so I can start planning the day ahead.
No, and there's also a way where you can do it without the Respondus lockdown browser. I actually allow you to do it, for instance, at the testing center if you prefer. So that's something else that's possible, but we'll
Okay.
see.
All right, thank you, sir.
You're welcome. So, I got two people. How's it going, Josiah?
It's going.
All right.
I was
Go ahead.
curious about the lab accoutrements and extra credit. I fear I probably forgot what you already said about it.
You don't have to worry about anything about lab accoutrements on our page because you guys are doing your lab with Miss Rashkovic. Uh, So that's where I normally put my labs if I was teaching the lab, but I don't have to do that. So there shouldn't be, ultimately, I'll remove all those. As far as extra credit goes, I just make up assignments from time to time and I'll put them in the week module that I make them. And the way they count is every time I add one, I add an extra drop grade to your homework. So it really just improves your homework score.
Okay, sweet, because that's like my worst part.
Yeah, that's sort of why I did that. The major extra credit comes from the practice test, so hopefully that'll work good. I'm adjusting some things right now. I was just telling Bohan that I found something that I think might be make it a little easier on you folks. So I'm now adjusting the dates accordingly. So, in other words, I'm going to not redo, but I'm going to continue doing chapter 17 today and finish up with chapter 17. And then next time, since we're off on Monday, it'll be another Wednesday, we'll go into 18. So I had to set all those dates back to do that. Looks like it's working so far. That shouldn't be too bad.
I have a question about the textbook real quick.
Yes.
Do you recommend just buying it like the through the Pearson online through the Canvas page? Is that the best option you'd say?
That's probably the cheapest. Obviously, I don't want to jockey for going against our bookstore or anything like that, but that's probably the cheapest way is going through there.
Okay, thank you.
No problem. Got some more people coming in now. Yee-hoo. Woohoo. Got another one. We're starting to get there. It's actually after time now, so I'm going to have to start in a second, anyways. Okay. How's everybody doing? Hopefully, everybody's doing well. I was just telling Josiah and Bohan that I decided yesterday on changing some stuff. So now I'm changing your syllabus again. That's why I haven't posted it yet. It'll be posted either tonight or tomorrow. What I decided to do, because I didn't realize we had Monday off immediately, and then later on we'll have June 19th off, Juneteenth and that sort of thing. So what I decided to do is, since we met 2 days this week, namely Monday and Wednesday, but Monday most of the time was spent talking a little bit about syllabus and doing very few examples, I decided to make this week just chapter 17. And now, since you don't have to come back on Monday, I moved the due date from Sunday at 11:59 p.m. to Tuesday at 11:59 p.m. And then next week, since we're off Monday, we're only going to attend Wednesday. That day we'll do chapter 18. And then of course that will be due at Sunday at 11:59 p.m. later. So I've adjusted those dates, at least for the first 4 chapters, and I'll be finishing the rest later. So you can now see them, and you'll see that chapter 18 homework, for instance, left module 1, and it's now in module 2, or module for week 2, that is. So that's the new plan. The syllabus will be up in useful links and documents, or whatever that module is called. So I'll send you an email when it's posted. But I do have, like I said, the homework dates are correct, at least through chapter 20 right now on My Lab and Mastering. Does anyone have any questions about any homework they've been doing or anything like that? All right. Well, I always try to offer the first 5, 10, maybe even up to 15 minutes to help you guys with homework problems that you've been working on. So if I jump into class and start talking and you have a homework question, by all means, stop me and say, hey, I got a homework question, because I just forget. I get excited about covering material and I just jump to it. So I would rather you guys ask me if you actually have a need for help on homework. So last time when we were here, we talked about basically we got into the ideal gas law and various ways you could use it. I talked about linear expansion and volume expansion. So I didn't really work any problems with linear expansion. I didn't work any problems with volume expansion. All I really did was work problems converting Celsius to Fahrenheit and Fahrenheit to Celsius. And we talked about how bimetallic strips use a thermal property of matter, namely that properties of, most substances expand when you increase the temperature. And they expand at different rates depending on what substance you're dealing with. So if you take 2 metals and bond them together, and then change the temperature, one's going to expand more than the other. So it'll go like this, in which case this is like the one with the high coefficient of expansion, whereas this one's the lower coefficient of expansion down here. And that will actually cause a metal to curl. Because of that, if you take a bimetallic strip and spiral it, you get a much longer one. And of course, the change in length is directly proportional to the length. So if you make the length, say, 4 times longer, then you should make the actual expansion 4 times longer as well. So by spiraling it up like that in a thermostat, we could actually see that it would, we can actually see that it will move accordingly and can be used not only to tell you the temperature about putting a little needle on there and calibrating it with various degree marks, but also it can run your system by completing a circuit with a little glass sort of capsule that has mercury in it. So that was kind of interesting. But I thought now I'd go back and cover some of the problems that we're going to do in chapter 17. In other words, cover a little bit more of what I originally planned. So when we meet Wednesday, remember we're off Monday. When we meet Wednesday, I'll start right in chapter 18. So right now what I'm going to do is cover chapter 17 some more. And I just realized something's missing. I'm filling out my document as we speak. So again, does anybody have any questions? Someone just posted on the chat, by the way, for everyone to see. It's Nora. So they do have a group chat thing going on that might be helpful to you guys. So by all means, do that. I want you guys to work together on your homeworks as much as you can and as much as you want to, at least. So just keep that in mind. I think study groups are a wonderful way to help one another. When we do online tests, that's the only time you're really not supposed to do any group help, or when we do, for instance, the midterm and final. So just keep that in mind. As long as you're not communicating stuff like that, you should be fine. All right, so I've now got everything up here that I needed to get up here, I think. Let's move page trash. That's good. One more time. All right, I think I got enough pages on here. Okay, so what I want to do first is I would like to actually work some physics problems for you. Specifically, I'm going to start with considering the expansion, say, of a 200-meter chunk of concrete. So one thing I want to mention to you guys about this is, have you ever heard of reinforced concrete? Anybody ever heard of that?
With like rebar in the middle or no?
Yeah, that's basically what I'm talking about. Yeah, so that's a game changer for us technologically, because steel is very strong when properly loaded. But if you take a really big, strong I-beam and you inadvertently stress it so that it contorts, in other words, suffers from some tension, like the top is rolling over this way, all of a sudden metal becomes like really, really weak. And it'll just, I actually saw after a hurricane, for instance, a big piece of I-bar over top of a area where you work on a car, basically in a garage, and the garage had been hit by probably a tornado. But what happened was it put a torque or a torsion on the actual I-beam, and because of that, the I-beam just sort of fell over, and you would be surprised how smooth it looked, like it was just made out of plastic, and it just got hot and melted and curled over. So that's the problem with steel. Steel is very strong and when loaded properly, but some ways that you load steel can be very bad. So if you take concrete, which has its problems too, it's not very good in tension, it's very brittle and compression. If you actually take the time to look at concrete, you'll see that that's got some downfall too. But it just so happens that the coefficient of linear expansion and the coefficient of coefficient of linear expansion for iron is about 12 times 10 to the 6, and the coefficient of linear expansion for concrete is about 12 times 10 to the -6 as well. Because of that, you can actually embed steel in concrete, and you can even do some things like stress the steel a little bit first. In other words, put it under tension, and then put the concrete around it, allow the cement to actually dry. The cement, by the way, is just the gluey part, and the concrete is the stuff that you talk about as a substance. But anyways, once that cement dries, the concrete becomes solid. It's now got a compressive strength applied to it from the compression of the steel, because you had to stretch the steel out. So that makes it even more strong. And since they have the same coefficient of expansion, in general, there's very little difference between how much the steel expands versus the concrete, whereas any little bit whatsoever that differentiates the amount of expansion actually deteriorates the material. So still over time, you're going to have reinforced concrete members failing over a long period of time. And that's because even if the difference is in the 18th decimal place, that's still a non-zero change in that. And I'm probably exaggerating with an 18th decimal place. It's probably a lot fewer than that. But that alone can actually cause the concrete to shake loose of the steel itself, and it becomes a little less helpful. Okay, so, and honestly, I was told once by a structural engineer, I haven't verified this myself because I never worked on bridges or roads. I only did buildings, commercial and private homes and buildings and stuff like that. But I was told that, for instance, if you build a bridge and you don't allow Mack trucks or tanks on it, then tanks, because they're about as heavy as a Mack truck, if you don't allow those on it, then that bridge will essentially last forever, assuming nothing bad happens to it from a hurricane or a runaway ship or something like that. Whereas just the fact that you've got the dynamic load of a Mack truck riding across it actually causes it to age. So over time, you generally have to replace bridges anyways. So that's just some extra sort of knowledge for those of you who are interested to some extent in engineering, especially if you're interested in, say, structural engineering, which was one of the areas I worked in. I worked in structural engineering at 2 engineering firms in the Outer Banks, and I also worked in electrical engineering at a company called Avanti, who's no longer exists. And I also did computer engineering there as well, where I was basically just writing code. So I have some experience in the engineering fields, but it's somewhat limited. I also did wastewater design, so we would design septic systems and stuff like that. I worked on the Kill Devil Hills water processing, or excuse me, sewage treatment plant. To actually, that was sort of my first introduction to doing engineering. So I've done some wastewater work as well, but that's about all I've done in engineering. Everything else has been physics. So feel free to ask me any questions if you're interested in any of that stuff. I just I try to share as much of it that I learned as possible, so you can really see if something's sort of interesting to you. I always thought structural engineering would be interesting to me, even when I was that horrible bad student in high school, just because we had our house fail while it was being built. Our builder was, ironically, I remember him. I was working for him at the time. A guy by the last name of Galbraith. He's passed away since then, but he's a friend of mine. But he's an old timer. He was funny. He drove an old one of those truck cars, and he drove that around with a big cowboy hat. And I remember we went to the permits office, and he had drawn the design for my house that he was building. He had drawn it on the inside of a cigarette carton and turned that in. Well, lo and behold, he hadn't thought out the design that well, and we had a cathedral ceiling like this with no cross members, and that caused the wall to fall out. When you design a truss, you're supposed to design it like with wheels on the bottom, so that you get no lateral strength from the walls, because they're really not very strong laterally. That wasn't taken into account. So what happened was we had like a 16-foot span of wall on each side of the house with no interlocking walls to hold it from slipping out. So the ridge beam just dropped in the middle, and the joists actually rolled out, or the rafters actually rolled out to the side and pushed the wall out. So the wall had fell probably close to 6 inches over an 8-foot high ceiling. So from the bottom of the 8-foot tall wall to the top of the 8-foot tall wall, it wasn't vertical. It had shifted almost a whole 6 inches out. And building inspectors saw that and immediately condemned the property, and we had to pay for some engineers to come fix it. And I was just in awe by the engineers that came in, and the very specific details that they wrote about how to fix it. So anyways, that's a kind of interesting idea. So let me go ahead and show you what we can do with linear expansion. If you've ever noticed when you're riding on a highway, you hear ta-kung, 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 ta-kung. You used to hear that really bad with trains. A lot of it, they've learned now that trains, you can put the track in tension and then weld it together, and you don't have to have expansion gaps anymore. Long as you put it in tension and try to do it on the hottest day of the year, you're not going to have any problems. But if you happen to do it on a cold day, yeah, then it's going to buckle, and you'll see the train track go like that all of a sudden. But they do the same thing with concrete when they're making roads. So if you make a concrete road, it's not unusual to have, say, 150 meters or 200 meters of concrete slab, and then they have an expansion break, and then another 200 or 300 meters of concrete slab. So what I'd like to do is do a calculation with that. What we know is, I'm going to go ahead and share my screen now. I think it's working, but it's going slow. Yep, there it is. Okay. So what we learned last time was that the change in length is equal to the coefficient of linear expansion alpha. It's also called the temperature coefficient of linear expansion times the initial length times delta T. What I'm going to do is consider a 250.0 meter, and technically, let me use proper literature or language. 250 meter should be hyphenated. Concrete slab installed at T equals, let's say, 20.0 degrees Celsius. If the temperature fluctuates between, let's say, negative 10.0, that's a huge cold spot, by the way, negative 10.0 degrees Celsius to positive 40.0 degrees Celsius, how much will the length change? So that's the question. All right. Now, what I can do is I can immediately look up alpha for concrete, and if I remember correctly, it's 12 times 10 to the negative 6. If you look at this units, you see the L's cancel out on both sides. So this has just got to be Celsius degrees to the negative 1 power. That's what the units are. Okay. And remember, we put the degree after the C because it's this number's plan is to be multiplied by a difference in temperatures. Is everybody on board with that? All right. So let's calculate what's going to happen. Has anybody been able to verify that it's the coefficient of linear expansion? If you haven't, it's no big deal, but I'm about 99% sure I remembered it right, because I think it's for concrete, it's like 35 for the volume expansion, whereas for steel, it's like 36 for the volume expansion. So really, really close. So here's our solution. What I'll do first is I'll do the cold temperature and see how that works out. So we're going to say delta T for the first part is going to be a negative 10.0 degrees Celsius minus a positive 20.0 degrees Celsius, which gives us negative 30.0 degrees Celsius. Okay. So that means delta L is going to be alpha times L0 times delta T, which gives us 12 times 10 to the negative 6 reciprocal Celsius degrees. And I think I might, well, nope, still the wrong page. I'm actually trying to pull up the book, so I'll have the verify. I'll be able to verify exactly what the coefficient of linear expansion is. That's not it either. You gotta go further back, up a little bit further.
I found the same.
Did you? Okay, that's cool. Thank you. Yeah, I just got to the table. It takes forever for the digital page to open up. So it's going to be 12 times 10 to the negative 6 times the initial length, which I said was 250.0 meters. And you're going to see why they don't really use this big of a slab in a second. And this is all going to be multiplied by negative 30.0. Now, technically, I wrote that wrong. Since I did a subtraction, I was supposed to write this as Celsius degrees, by the way. So that's what I'm going to do now, Celsius degrees. Again, it's a pedantic thing. It just helps you keep track of what you've done versus what you haven't done. So don't worry about me taking off points or something if I don't see you doing that way. It's not like that at all. Okay. So when I do this math, I get 12 times 10 to the negative 6 times 250 times negative 30. And it looks like there's only 2 sig figs that I'm going to get here. So this is negative 0.090 meters. Okay, and it comes out in meters because I put it in meters. Now you can make this into centimeters via conversion, and you'd see that it's basically 9.00 centimeters negative, which means it shrunk. And that's what you expect. Is normally when things get colder, they get smaller, and when things get hotter, they get larger. So that is delta L for the cold temperature. Now delta L, I'll write cold up here too, so it doesn't look like I made up an equation that's not equal to itself. I'll say delta L hot. That's going to again be alpha L0 times delta T, which again is 12 times 10 to the negative 6. Now, when you're really doing this large a range of temperatures, it's probably worthwhile if you're actually designing for an engineering firm, you know, doing real work. You should probably look up what the linear coefficient of expansion is, say at 40 degrees. If they have that, they sometimes will have it at like increments of every 5 degrees Celsius. So you could do that, and you want to use the appropriate value for each stretch. So you might say, okay, well, I'm going to use 35 to go from 30 to 40. I'll use the 20 to go from let's say 20 to 30, and then I'll use the 0 degrees to go from 10 to negative 10 or something like that. That way you're honing it in with the best of the data. Right now I'm going to do this, centimeters to the negative 1 times 250.0 meters times, in this case, it's going to be like the delta normally means, it's final minus initial. So this would be 40.0 degrees Celsius minus 20.0 degrees Celsius. So that gives me Celsius degrees. So I'm going to say 40 minus 20. I don't have to put that in my calculator, obviously. It's positive 20 times 250 times 12e to the negative 6. And that gives me 0.0600. Again, I'm only using 2 sig figs, so I'll underline that third digit. Now, again, I can also make this positive 6.00 centimeters. So it shrunk by 9 centimeters, but then came back and went up by 6. So in fact, the total change in length is about 15.00 centimeters. Now, since we're adding, remember the sig fig rules for adding is you round it off at the add-in that had the fewest decimal places. In this case, the fewest decimal places was 1 decimal place in all cases. But because I added 9 and 16, I got a double-digit number, which allowed me to now have 3 sig figs instead of just 1, instead of just 2. Okay, so that's the ultimate answer. Anybody have any questions on that? All right. Here's another fairly neat problem we'll work on. This time we're going to do a volume expansion. And I hinted at this before, and your book solves a similar problem. What we're going to do is assume that we have a steel gas tank. And the steel gas tank, this will be example 2. a steel gas tank is empty, but can easily hold, let's say it can easily hold, let's say 10 liters. Let's say 15 liters. At, let's say 10.0 degrees Celsius. When the temperature reaches, let's say 40.0 degrees Celsius, the tank volume will behave as if, or I should say, let's do it a different way. I'll say it will behave as the missing metal would. Let's say steel, actually. So what I mean by that, this is also referring somewhat to an example in the book where they ask you conceptually, let's say you have a ring like this, so y'all can see me in my little picture, and you have a ball that just barely fits in the ring, right? If you were to then take that ring and heat it up, what we've learned with these expansion laws is that every dimension increases when you heat it up. So does that suggest that the inside of the ring will get smaller? Or does it suggest that the diameter of the inside of the ring actually gets larger? We know the outside diameter is going to get larger, but what about the inside diameter? Anybody know that answer?
It gets smaller.
Yeah, that's what I would think, but it turns out no. And that's why I worded this answer this way. So it's good that you answered it wrong. I thought the same thing myself. But in fact, what happens is that ring, you can imagine, might have started off from a machine shop as a flat piece of metal with no hole in it. And then you take a press and you pop out the inner ring. Well, it turns out that hole acts just like the inner ring would, or the inner disc of circular metal would, if it was still in there. So that tells us the inside of a hole actually expands too. So if you amp that up from a 2-dimensional circle to a 3-dimensional gas tank, the gas tank's going to expand as well, such that the volume inside it gets larger. So how much gas will overflow if 15.0 liters of gasoline filled the tank at 10.0 degrees Celsius. Okay. Everybody understand what's going on here? Anybody not understand this problem? Okay, I'm going to go back a page on this book. The coefficient of expansion for gas is a beta value, and I think it's 30, no, it's like 2000 or something. I can't remember. Let's see. gasoline, 950. So beta, which is usually approximately 3 times alpha, but for a liquid that doesn't make sense, is actually beta is actually equal to 950 times 10 to the negative 6 reciprocal Celsius degrees. Okay. Delta B, or excuse me, delta V is equal to beta V0 delta T. So first off, I'm going to do delta V for the tank, which is made of steel. And that's 35 times 10 to the negative 6. So beta is 35 times 10 to the negative 6 Celsius degrees reciprocal. The initial volume is 15.0 liters, and the change in temperature is 40.0 degrees Celsius minus 10.0 degrees Celsius. So again, I just do the arithmetic. I'm going to say 35 e to the negative 6 times, oh, I was supposed to say 950. I don't know why. Oh, that's right. I'm doing the tank. Sorry. 35 times 10 to the negative 6. Times 10 to the negative 6 times 15 times 40 minus 10 is 30. So in this case, I get 0.01575. And since the units went in as liters, the units came out as liters. Here I only have 2 sig figs, so this 7 and 5 are both not allowed. Okay, so we know it's going up by basically 15,000th of a liter. So the gas tank is going to expand as a result of the higher temperature too. It's just not going to expand very much. It expanded 0.015. Now what we need to do is figure out how much the gas expands. And if we assume that it really could only hold 15, then any amount over 15 plus 0.01575 liters is going to be spilled. So now let's look at delta V for the gas. That's going to be, again, I said 950 times 10 to the negative 6 Celsius degrees to the negative 1 power times 15.0 liters times 30.0 Celsius degrees. In other words, it's the same subtraction, so I didn't need to write it out so bad. So 950 times, or excuse me, 950 EE negative 6 times 15 times 30 is going to give me 0.4275. This one, we sort of think we had 3 sig figs, but we might have only had 2. I'm going to assume that 950 only represents 2 sig figs, and therefore I'm going to make those, the 7 and the 5, as not valid sig figs. Okay. So the new volume of the tank is equal to 15.0 liters plus 0.01, let's call 58 liters that. And obviously, well, actually, let me do it this way. I did not plan wisely. I should have acted like I knew this to 2 sig figs. So you guys go ahead and change that and make it 2 sig figs. So now we're golden. See, everything was perfect the whole time. I don't know what y'all are talking about. Okay, so this is going to be 15.00 liters plus 0.0158, and that 8 is an extra sig fig that we don't really have, so it's not a significant figure. So we'll now say the new volume is 15.0158. And again, we're really looking at only those last two digits as being not significant. So that's the new volume. The new gas volume is 15.00 liters, which I'll put that 0 in there, and it's going to be plus 0.428 liters. And of course, that gives us 15.428 liters. So if you do 15.428 minus 15.0158, you get 0.412 liters spilled. So you're losing almost a half a liter of gasoline by filling it up when it's cold and then allowing the day to get hot. Any questions on that one? So hopefully that makes some sense to you. Go ahead.
Oh, I'm sorry. I was still trying to copy stuff down earlier, but can you explain how we got beta equals 3 alpha?
Okay.
Okay.
That's actually from the reading of the textbook. It turns out that we predict it theoretically, and it turns out to be pretty close experimentally, that the beta value is about 3 times the alpha value. In this case, I was just stating that to let you know, hey, this is something that you should have gotten from your reading in case it pops up in a conceptual question. So that's why I wrote it at all. In reality, all you needed to pay attention to was this part right here that I waved. Because if you look at that table for actual gasoline, you'll see that there's no alpha listed. That's because gasoline's a liquid and you can't have a rod of gasoline. So yeah, that was just me. It's probably pedagogically not sound, but you know, when I think of something that you guys need to know, I usually tell it to you right then or shortly thereafter. So that's what happened. I just took the time to point that out in case you didn't read it or in case you missed it in your reading.
Okay, gotcha. Thank you.
All right. No problem. Make sure you ask those questions. Those are really good questions. Just to understand what's going on with this. So your book does do an example, like I said, with a hole and a thing pointing through it. You can also do other problems, like your book does one where it says, okay, you have a ring that has a diameter of 6.445 centimeters, and you have a diameter of a rod is 6.445 centimeters, and the diameter of a ring, the inner diameter, is 6.420 centimeters. And what they want to know is if you assume that you have to go 0.008 centimeters larger than the diameter of the rod to fit the rod in, at what temperature would that rod, which was made of iron, have to be raised to make it fit? Okay. So that's another type of problem you can solve as well. Let me give you something equivalent. So we'll say, go ahead.
Question.
Yes.
Regarding, I don't know what they're called, but the 950 and the 35, are those not 3.5 and 9.50?
Yeah, in the table, they're literally 35.
Oh, okay.
Yeah,
Sorry about
yeah, they just they like the fact that all the powers were powers to 10 to the -6. So that's why they left it that way. Hell, Ron, did you have a question?
Yeah, I'm sorry. It's about the question before that I forgot to ask earlier.
Okay.
But when we got the delta length for cold and delta length for hot,
Mm-hmm.
that's to find the difference, right?
Right.
So would it be delta hot minus delta cold, or delta cold minus
Which you're talking about the concrete slab, not the gasoline, right?
Yes, because delta cold was -9 and then delta hot was 6, but the total like delta was 15.
You're right. So yeah, what you had is like the end of the rod. If you look at me, the image of me as opposed to the writing, the end of the rod was right here. When you made it colder, it went all the way back to here. Or I say the rod, the end of the concrete slab was here. When you got it colder, it went all the way back to here, where all the concrete's back there. And then once it got hotter, it went all the way out to here. So that's what we needed. And that was basically a -9 and then 9 in magnitude and then a +6 on this side. So you really had to sort of don't blindly subtract or add. What you really want to do is think about what's the distance from the end when it's at its shortest to when it's at its longest. So I just quickly went through that in my head and chose how I was going to subtract it. I did 9 + 6 instead of, or excuse me, I did 6 + 9 instead of 6 - 9 or anything like that.
Okay, so we just do the absolute value of
Yeah,
those two?
it all depends on how the wording is, and that's the key point. If I asked you what was the total change, because what I was imagining in my head was how much filler are you going to have to put between that slab and the next slab? Well, what that is a slab that's big enough to fill in the gap when it's at its smallest to when it's at its biggest. So I had to think I need to go 9 this way plus 6 this way. That gave me a total of 15. So it's literally 15 centimeters of soft goo between the things. And you can imagine that's sort of a nightmare, especially if you're talking about a bridge where you usually secure the concrete slab at the ends. Obviously 15 centimeters is a lot of end that you have to account for. Does that help you more?
Oh yeah, no, that's good. Thank you.
No problem. Also, pay close attention to that when you start doing the multiple choice problems. A lot of times you'll run into 2 problems or 3 problems or 4 problems that all look identical, but there's like one little word changed. And that one little word makes such a big difference that the answer is entirely different. So you do got to pay close attention to the wording. And not all of them are that well worded, to be honest with you. I try to remove those every semester, but of course I find a new one just about every semester. So let me know if you find the wording on any of them nasty. You can take a screenshot of it, let me know, and either I'll explain it to you how it's supposed to be read, or I'll actually make the change. Okay. All right, so I'm gonna go, instead of doing the rod fitting into the ring, I'm gonna talk about the conceptual idea that it has with opening a jar. So in your book, they talk about maybe if you have a jar of pickles or something like that. I think they actually had some kind of it looked like some kind of Indian sauce, biryani paste. Yeah, it looked like a curry sauce or something. But anyways, if you ever have a jar like that that's hard to open, what sort of happened, especially if it's old, if you've got something that's really old, like expired old, what's happened is botulinum is built up in there, and botulinum produces a gas, and then that gas makes a super high pressure. In fact, when I moved into my graduate office at Chapel Hill, there was a can of soup that had been there from like a winter storm 10 years prior, and we just sort of kept it as a matter of pride. But at this point, the can of soup, which had expired like in 93, and this was 1999, it was almost spherical because the botulinum had expanded so much that it made it almost like a round ball. So that's sort of what happens. Even if it's not botulinum, there can still be a pressure because they might have actually bottled it in a colder temperature environment than it is in now. So if you need to do that, what you can do is run the water hot over the metal lid. When you run it over the metal lid, like the picture shows in your book, then the water mostly hits the metal and very little hits much of the glass. And luckily, glass doesn't nearly expand as much for a given temperature change as does metal. And Pyrex glass is even better at it. But the main thing is, even if you get some on the glass, it's not going to matter that much because the metal is going to expand more. That actually loosens it up so where you can dry it off rather quickly and then loosen it. So that's the conceptual idea behind that. And we now know that based on what I started with, just talking about the laws of atomic theory, which basically says matter is made up of these little vibrating balls. So we already figured out, yeah, we expect them to expand when they increase the temperature, and we expect them to contract when they decrease the temperature. So we already knew that kind of stuff. We also did do a calculation, by the way, of what volume 1 mole of gas takes up at standard temperature and pressure. And we found that was 22.4 liters. I did do that calculation with you yesterday, didn't I? Let me double check. I have 2 classes of this section going, so there's some probability that I forgot. And it looks like I did not do it, or did I do it? No, I did not do it. I do not see it anyways. All right, so let's work that one, and then we'll go on to doing more stuff with the ideal gas law. Yeah, I don't see that I did it there. Okay. So let's work an ideal gas law. What I want to know is what, this would be example 3, by the way. What is the volume of 1.00 moles of an ideal gas at STP? That's called standard temperature and pressure. If you've had chemistry, you probably already knew that. If you had chemistry, though, you might have also made the same complaint as I did, which is standard temperature and pressure, I would assume, since it's coming from a science class, has some bearing on the conditions within a lab. And I've never, ever, ever had to work in a lab that was 0 degrees Celsius, but clearly that's what they're thinking. So standard temperature and pressure means the temperature is equal to 273.15 Kelvin, and the pressure is 1.013 times 10 to the 5th Pascal. So that's what the standard temperature and pressure are. The ideal gas law says that PV is equal to nRT. So our solution would be, let's solve for V. And V, of course, is equal to nRT over P. N is 1.00 moles. R is 8.314 joules per mole Kelvin, and T is 273.15 Kelvin. Remember the ideal gas law, 1 has to use temperature in Kelvin, 2 has to use the absolute pressure, not the gauge pressure, and 3, you also have to choose the right value of R depending on what units you use for those other things. So the pressure is going to be 1.013 times 10 to the 5th Pascal. And now I get the following answer. It's going to come out in cubic meters because the joule is a Newton meter, which you hopefully remember from 241. The moles canceling out with the mole in the bottom, and the kelvins canceling out with the mole in the bottom. The joule is a Newton meter, and the Pascal is a Newton per meter squared. So that becomes, since the Pascal's in the bottom, that becomes meters squared per Newton in the top times Newton meters. So that gives you meters cubed. So that's how the units work out there. Hopefully you can see that in your head. If you don't, it's not a big deal. Just try to work it out by writing it. So I'm doing 8.314 times 273.15, and then I'm going to divide that by 1.013 e to the 5th and that gives me 0.0224. Okay. Now I put in 4 sig figs, 3 sig figs, 5 sig figs. So really it looks like 3 sig figs is what we're limited to. So I'm going to call that digit right there doubtful, or excuse me, that digit not significant. And this is cubic meters. By the way, 1 liter has a very specific definition. 1.000 liters is represented by 10 centimeters by 10 centimeters by 10 centimeters. So the volume of 1.00 liters is 10 centimeters cubed, which equals 1,000 cubic centimeters. That's pretty helpful, but not necessarily that good. If you divide a liter by 1,000, we also know that you'd have 1 milliliter, because that's the definition of a million is, or of a milli, is to divide by 1,000. So if I take the left and divide by 1,000, I get 1 milliliter. If I take the right and divide by 1,000, I get 1 cubic centimeter. So that's a centimeter cube. So that's a number, at least when you guys decide or possibly ever have kids, you will see that some doctors will prescribe cc's of medicine, some doctors will prescribe milliliters of medicine, and some pharmacists will do milliliters, and some pharmacists will do cc's. And they might literally do one going into the pharmacy and another coming out. And I don't want you to flip out, because now you know that a cubic centimeter is the same as a milliliter. Now, the other thing is, how is this related to a cubic meter? Well, if you took a 1 meter box by 1 meter by 1 meter, that's going to be 1 cubic meter. Okay. Well, it turns out that 1 meter is actually equal to 100 centimeters. So if I want to actually convert to units, I need to raise that conversion factor to a power of 3. And what I find out is that that is in fact 100 times 100 times 100. That's 1 million cubic centimeters. Okay, so 1 cubic meter is 1 million cubic centimeters. 1,000 of those, of course, is a liter. So now I can say 1,000 liters. So 1 cubic meter is 1,000 liters. So if I multiply this number by 1,000, I get 22.42 liters. And that is an important finding, in that that's a rule of thumb that physicists and chemists use all the time. We always expect a gas to take up a volume of 22.4 liters for every mole of gas that you have at standard temperature and pressure. Any questions on that one? Now, it looks like we don't have any questions for that, but can anybody tell me, hopefully you probably remember it, or at least remembers the numbers you need. Can anybody tell me what the molecular weight of water molecule is? And I'll put quotation marks around it because it's technically not weight, it's mass.
Is it 18 AMU?
Yes, it's 18, because hydrogen is 1 essentially, and oxygen is 15.9994, which is essentially 16. So yes, the answer is 18.0 grams to that many decimal places is good. So that means grams per mole, by the way. So if you take water and you heat it up to 100 degrees Celsius, it starts to change state and it becomes a gas. Now, as a gas, water vapor is an ideal gas, at least around 0 degrees Celsius and quite a few higher temperatures as well. So water will actually take up about 22.4 liters as steam. So 1 mole of steam at STP, and now that's a big if, by the way. Okay, but I'm doing this for a reason. Standard temperature and pressure might not sustain water in the liquid state. I mean, in the gaseous state. So it might not be possible, but I wanted you to have some feel for how much more dense a liquid is than a gas. So if you think about this, 1 mole of steam has a volume of about 22.4 liters, but the density of water is equal to 1 gram per milliliter, or 1 gram per cubic centimeter. Okay. So how many liters does a mole of water take up? Anybody guess that one? We found out the mass of a mole of water because Nora knew it was 18 grams. I just gave you the density as 1 gram per milliliter. So how many milliliters should a 18 grams of water be? How about 18? Okay. So the reason I'm pointing this out is obviously there's no real physical meaning to it, because if you really tried and held water at 0 degrees Celsius at atmospheric pressure, it would certainly not be in the gaseous state, right? But I wanted you to have some sense of how far apart the individual atoms and molecules are in a gas versus what it is in a liquid, which is still a lot bigger than what it is in a solid. So you can see now that if this number was, instead of 18, if that number was 22, then the steam would take up 1,000 times more volume than the liquid did. But since the number is 18, it's actually even more than 1,000 times. In fact, it's 1,220 times more volume. So 1,222 times the volume of liquid is equal to the volume of the gas. So if you take the cube root of that, that would suggest that the molecules are going to be on the order of 1,000 times further apart, because the cube root of 1,220 is, 10.7. So it's about 10.7 times as far away. All right. Any questions on that? Does everybody get what I'm saying there? Do y'all see how that pertains to the calculation we did on Monday regarding how far apart the copper molecules were? Or I think I did steel, didn't I? Yeah, I did steel. All right. So we did that. Now what we're going to do is I'm going to talk a little bit. I'm going to stop sharing my screen for a second and talk to you about something interesting about water. Hopefully you've heard it before, but this is one of those things I often tell my students that we have this sort of neat scenario where there's these fundamental constants of nature, like the electron charge or the gravitational constant of the universe, from Newton's law of gravity, or the ideal gas law, stuff like the ideal gas constant, stuff like that. Those are very specific constants, and some of them, not necessarily the R, for instance, but some of them are very important in the sense that if they were off by a couple percent, then life could possibly not have existed at all. You can literally do calculations and show that if, for instance, the K value, which is like the G value in Newton's law of gravity, there's a K value in the Coulomb's law of electric forces. If that K value was slightly different, then hydrogen might not be stable. And if hydrogen is not stable, you can't have nucleosynthesis where hydrogen combines with hydrogen to make helium, and then helium combines with helium to become carbon, and then carbon combines with carbon and other things to become silicon, and so on and so forth. So we quickly don't have the elements necessary for life because we can't do the nuclear physics that goes on inside the star's core, as well as in supernova explosions. So it's really kind of interesting, and I describe it to my students. Also, when we're talking about quantum mechanics, I describe it in that realm as well. That it's like God left a little step ladder, whatever God you want to talk about, left a little step ladder where you can walk up the little step ladder and look over the bar into the sink and just see enough to understand. Okay. That's exactly what happened with regards to quantum mechanics when we were developing that. Bohr was able to see from de Broglie that matter should have wave-like properties because that's what de Broglie hypothesized. Whereas before we had just shown that light can be a particle, where we had thought about it being a wave forever, or at least for a long time. So when quantum mechanics first comes on the stage with photoelectric effect and with the ultraviolet catastrophe, we were having to deal with what we had finally convinced ourselves light was, which was a wave because of Maxwell's equations, Huygens principles, all the equations that we had found from optics and that sort of stuff, all pointed to light being a wave. But the only way we could explain the ultraviolet catastrophe away and come up with a distribution of matter, or excuse me, of energy and wavelengths, was by introducing the concept of light being made up of particles. Okay. Well, de Broglie took that and said, I can't imagine a universe in which God creates this duality on light, where light sometimes behaves like light, i.e. its wave behavior, and other times behaves like matter, i.e. its particle nature, right? He could not imagine that the universe would be made that way if the opposite wasn't also true, meaning he expected, just purely from that symmetry, that matter, which we've always treated as a bunch of little itty bitty particles, are going to have a wavelength. And he basically used dimensional analysis to come up with what that wavelength was. And it told him, okay, we have this wavelength. Well, that made Bohr think, oh, wow, if I think of an electron as having a wavelength, then maybe the electron in orbit around the nucleus is only a stable orbit if the distance around the orbit is one wavelength or two wavelengths or three wavelengths or four wavelengths, not unlike what you learned in chapters 14 and 15. Okay. So again, this feels like Bohr was able to look over and see just enough information that matter might be made of waves, that he could think in terms of electrons being made of waves, and therefore he made the Bohr model of the atom such that the first orbital was 1 electron wavelength, the second orbital had a circumference of 2 electron wavelengths, the third had 3 electron wavelengths, so on and so forth. That's wonderful because it turned out to be exactly right. It gave the exact right answers of what we knew from tubes that are like neon tubes nowadays, okay? Except these were tubes that were filled with hydrogen or mercury or something like that. So he won the Nobel Prize for that, and that was because he got that little insight. But also because Schrodinger got that one little insight, Schrodinger was able to hypothesize that maybe matter that we want to describe with quantum mechanics must obey a wave equation. And from that, he was able to derive Schrodinger's equation. Now, it turns out that ultimately Bohr's model of the atom is more or less completely wrong. It just happened to be coincidentally exactly the right numbers that would come from assuming that the electron was doing what he suggested it was doing, but it was completely wrong. But it was right enough to make Schrodinger think of a wave equation that turned out to be the exact right equation. And then later we had to look back at what the Schrodinger equation was giving us and decide exactly what that meant. Okay, so this is sort of the same thing. We have basically this neat property of water that just allows life to survive. And what it is that water has a density that is a bit weird, okay? Generally speaking, everything gets less dense as the temperature goes up, goes up, goes up, goes up. Well, check this out. If you take the temperature, if you take water at a temperature of 0 degrees, it's basically ice, which is less dense than the solid. That's another weird thing. Normally, a liquid of one substance will not cause the solid of the same substance to float in it, but water does that. Now, if you take that water at 0 degrees Celsius and you raise the temperature, lo and behold, it actually contracts. It gets smaller and smaller. In other words, the density gets higher and higher until it reaches 4 degrees Celsius. That's when the density of water is a maximum, is at 4 degrees Celsius. If I keep going up in temperature, then water starts to behave properly and the density starts to fall because it's expanding. But that little bit of area there allows life to live in even the shallowest of ponds during an ice age, because the most dense water is the water that sits at the bottom, and the most dense water is the water that happens to be 4 degrees Celsius, where water is still a liquid, not a solid, and therefore life can still exist. Isn't that cool? All right, so that's sort of the big concepts that I wanted you to get from water. And I also like the sort of our course, astronomy at least. And when we get into the cosmology section of this course, if you ever get to it, it constantly has to bump heads a little bit with religion. And I don't believe that has to happen. Okay, so that's why I'm trying to let you know that doesn't have to happen. Religion talks about thing A and science talks about thing B. And if you don't use religion to try to dictate science, and you don't use science to try to dictate religion, you can get along with them perfectly fine. So I like to bring in that analogy about seeing the step stool and stuff as often as I can, just in case people get thrown off or start to dislike science and astronomy because it seems to contradict some of the stuff that you believe or some of the stuff that your preacher or whatever taught you. Okay. So anyways, I will get off of my other version of a soapbox, which is trying to have a kumbaya moment between scientists and religion. Anybody have any questions on that? Another thing that I do, for instance, is I let them know the first person that really hypothesized, well, the first person that we knew of at the time that hypothesized a Big Bang was a Jesuit priest. And in fact, when the Pope heard about his Jesuit priest predicting a primeval atom, he was like, wow, this is great. This really proves the book of Genesis is right, which somehow from that 1920 era to now, it's become completely flipped on its head where everybody says the Big Bang and all that stuff is the antithesis of religion. It doesn't have to be. Okay. The other guy, by the way, that predicted it was a guy by the name of Alexander Friedman, who was a Russian and probably an atheist, just knowing what we know about most of the Russians in that era. But anyway, he might have been an atheist. But the main thing is he both him and the Jesuit priest came up with the same hypothesis. Just Russia was a bit of a backwater at the time, and they were going through some turmoil. So information didn't come out till well after the Jesuit priest's information came out. So I'm trying to remember the Jesuit priest's name now. Oh well, I might think of it later. I might not. But there's some good books on it. Anybody have any questions on that? Lemaitre, Georges Lemaitre. That was the name of the Jesuit priest. All right, let's go start by sharing our screen again. And we're going to solve some more physics problems because that is the awesome thing that we do. Okay, this is supposed to happen any minute now. There it is. Okay, we're back online. So that there is a section in your book called Anomalous Behavior of Water Below 4 degrees Celsius. That was what I was just discussing, and I was giving you my own sort of spin on it. You can see the graphs and all sorts of cool stuff. You can see life under ice is one of the claims that they make. That's kind of neat. But what I want to do is go ahead and work a couple more problems. One, I want to tell you about, we don't normally cover stress and strain and moduli in our physics, calculus-based physics. That is something that's extremely important to material scientists and materials engineers and structural engineers and stuff like that. I will tell you that in general, there's a concept called a modulus. And modulus is always defined to be stress over strain. So, for instance, there's a Young's modulus. And that's what you have when you deal with, let's say, a rod being stretched or compressed. The ability of that rod to exist, that compression or that stretching, is something related to the Young's modulus. So now I'm going to show you that Young's modulus E is in fact stress over strain. Now, what I use to help me remember this is stress has the same 4 letters in it as pressure does. Can anybody tell me what 4 letters I'm talking about? Stress and pressure. Yeah.
RESSE.
Yes, the RESS. So that can be your model that you use to remind you that stress is actually something related to a force. And in this case, it's a compressive or expansive force, and it's force divided by the area perpendicular to the force. That F over A perpendicular is the definition of pressure. So that's why it helps me. And then the strain is really a deformation. So this is a deformation. In other words, you're changing its shape. And this is like pressure. So in this case, for the Young's modulus, it'd be delta L over L0. So that's what we mean when we say the modulus is stress over strain. There's a shear modulus. There's a Young's modulus, which is really about compressive strengths and stuff like that. But there's also a bulk modulus, which is like compressing a volume. Your book does in section 17-5, it does thermal stress. In other words, you can say, imagine you put a rod between, let's say, two concrete blocks, and you pried it in there really, really good, right? Now you did that at 0 degrees Celsius, and then all of a sudden the temperatures now reach 40 degrees Celsius. So the rod really, really, really is trying to expand, but it's got a ginormous building on each end. Well, if you want to know exactly what pressure that rod is putting on it, you say pressure, which is equal to force divided by the area over which it's applied, which would be the force over power squared if it's a circular rod. That is equal to Young's modulus times alpha times delta T. So you can now use that formula, even though I try to cut all those questions out of the practice test bank, because I'm not going to ask you questions on that for the test or the midterm or the final. So but I wanted you to know it just because it's so important to engineering. I wanted you to know where it came from. Okay. So that stress is the stress that causes concrete to buckle. That's why you often see sidewalks cracked. If you don't put a large enough expansion barrier between two long pieces of concrete, then when the temperature gets high enough, they're going to force themselves against each other. And it's actually going to ultimately, no pun intended, ultimately exceed the ultimate strength of the substance, and therefore it will crack. Okay. Any questions on that?
I had to rewrite part of my notes. Would you be able to reiterate what was going on with the weird double hook in the 17_5 thermal?
Yeah. So that double hook means subsection. It's just two S's strung together. So that's fancy lexicography of subsections. So if you put an S and then you make the bottom of the S the sort of circular loop part of the top of another S, then that's the symbol we use for subsection. So I'm just saying subsection 17.5 of your textbook is what we call thermal stresses. So that's where I'm actually, the part of the textbook that I'm actually talking about right now is section 17-5. That good? All right.
Yep, thank you.
No problem. So now we can do some more ideal gas law problems, but there's some reading that needs to be done. So if you look at subsection, that's the, SS inner hook or whatever it was you called it, that's section 17-6, the gas laws and absolute temperature. An ideal gas law is something we call an equation of state. An equation of state is any equation that relates relevant variables to one another. So in the case of the ideal gas law, it relates pressure, volume, temperature, and number of moles to each other. It turns out that's all the variables we need to specify the state that a gas is in, as long as the gas is in equilibrium. If the gas is not in equilibrium, we haven't really found a good way to deal with that. So equilibrium states are sort of necessary, and the state equation is an equation that relates the state variables. So anytime you look at a system, it's going to have a certain number of variables that you have to take into account to fully describe it. You never know exactly what variables they are until someone else has done it for you or until you take it out. So for instance, there's actually an equation of state for a rubber band. And the rubber band depends on essentially the temperature and something like a spring constant. And we actually have worked out the equation of state for a rubber band, and we can use that to analyze problems in thermodynamics and stuff like that. So that's one of the hallmarks of science, is ultimately you take something that you want to understand. In the case we were talking about, ideal gases, or just gases in general, because all gases behave like ideal gases unless the density is too high or the temperature too low. Then they start to deviate from the ideal gas law. Similarly, if we wanted to understand a rubber band, we'd have to put some thought into what variables are affecting the state of the rubber band. And you can actually look that up. In fact, that's often what we do in a graduate level course. But the equation of state relates the state variables to one another. And we happen to have discovered one for gases that works pretty well. And it started off with Boyle's law, where Boyle found that pressure and volume are inversely related. I've told you that's the scuba diver's law. That means if I'm at, let's say, 30 foot of salt water, the pressure around me is 2 atmospheres of pressure, which is 2 times 1.013 times 10 to the 5th Pascal, or about 29.4 psi. Now, if I go from 30 foot of salt water to 0 foot of salt water, the pressure is going to drop to 1 atmosphere, or 1.013 times 10 to the 5th Pascal, or 14.7 psi. Well, since I went from 30 feet to 0 feet, the pressure actually went down. And if I was stupid enough to hold my breath when I did that, I would die. Okay. What would happen is my lungs would expand to attempt to expand to double their volume, because I cut the pressure in half. So the volume would go up by a factor of 2, and that would kill me. Almost certainly, if you do a rapid ascent from 30 feet to 0 feet, and you had taken a breath at the 30 feet, you are going to die. Okay. So don't do that. And that's why they call it the ideal gas law, or excuse me, that's why they call it the scuba diver's law. And the rule is to counteract that: never hold your breath, never hold your breath, never hold your breath. So even if you have to ascend because you ran out of air, what you want to do is constantly exhale. And it's not as hard as you think, because as you get higher and higher, the gas in your lungs is expanding more and just filters out of your throat. But that was Boyle's law. It took over 100 years before we got another relationship. And that relationship was Charles's law. And Charles's law found that the volume and temperature were linearly related. I used a graph similar to Charles's law, except Charles's law is volume versus temperature, and I did pressure versus temperature to tell you what the absolute value or the absolute zero meant. You can see that again in Charles's law, because of volume on the vertical axis with temperature on the horizontal axis has the same sort of line, and all the lines, no matter what gas you're using, all converge at the same point on the t-axis, negative 273.15 Celsius. Okay. So that's where we get the absolute zero. That's Charles's law. As I said, that was like a whole 100 years after Boyle. Boyle lived from 1627 to 1691. And then Charles was not born, Jacques Charles was not born until 1746 and died in 1823. So you can see it's a huge time gap between them. After that, another guy comes along. He was born in 1778, so he was more or less a contemporary of Charles, even though he was about 30 years younger. They at least had an overlapping life. And he found that pressure and temperature were directly related. You could put all that together and use the fact that we ultimately figured that mass is directly proportional to temperature. And since mass is directly proportional to temperature and the number of moles is directly proportional to mass, then the number of moles would be directly proportional to temperature. And since the number of atoms is directly proportional to the number of moles, we can say that the number of atoms is directly proportional to temperature. So what we have now is P is inversely related to V. That's Boyle's law. We have V is directly related to T. That's called Charles's law. And we have P is directly proportional to T. That's Gay-Lussac's. I think it's L-U-S-A-A-C. Yeah, it is. No, it's L-U-S-S-A-C. That's what it is. And then ultimately, we also are able to figure out that M is proportional to T and N is proportional to T and big N is proportional to T. So that gives us two versions of the ideal gas law. PV equals nRT and PV equals big N KT, where K is often subscripted with a B, and it's called the Boltzmann's constant, and it's actually R over Avogadro's number, which is about 1.3807 times 10 to the negative 23rd joules per Kelvin. I think, if I remember correctly. I will double check that to make sure. All of a sudden I wrote it down. I'm looking and thinking maybe the 23 is not right. So 1.3807 times 10 to the negative 23rd. Yeah, that sounds right. So it's probably fine. Okay. Your book does do a nice conceptual example. It says, why should you not put a closed glass jar into a campfire? Remember what I told you about gasoline versus a metal? The metal, or about glass versus a metal too. The metal is not going to expand as quickly as the gas, and the metal is going to expand quite a bit quicker than the glass, GLASS. Okay. So if you take a jar and you put a lid on it, it has trapped air inside. Air is a gas. If you lay that inside of a fire pit, the gas is going to expand and do so way faster than any solid will. So you've basically just made a bomb. Okay. It's not that dangerous of a bomb in that you're only hitting people with shards of glass that could cut you to pieces, as opposed to radioactive elements and radiation and stuff like that. But still, it's a valuable conceptual thing to know about physics. So I went with it. Now, I've talked about the ideal gas law. I've reminded you how to actually convert grams to moles. So for instance, if you want to know, let's see, I think your book might have given me a good example. No, that was not a good example. Oh, CO2. Yeah, that's a good example. So let's convert grams to moles. And I'm using the word convert there. They're fundamentally different quantities. Gram is a measurement of inertia and mass. A mole is a certain amount of mass for a certain thing, and it really is Avogadro's number of atoms. Okay. So if you take, for instance, CO2, what you find is that carbon has a mass, a molecular weight. Actually, let me do it this way. The molecular weight of carbon is equal to 12.01, if I remember correctly. That's close enough. 12.01 grams per mole. And oxygen, the molecular weight of oxygen, is essentially 16.00 grams per mole. So the molecular weight of CO2, I think you can see, since the O2 is there, that's going to be 32 grams for the O2. and then 12 grams for the carbon. That gives me 44.0 grams per mole. So that's the molecular weight of CO2. Now, what if we had 120 grams of CO2? How many moles of CO2 are in 120.0 grams of CO2? Well, all you have to do is take that 120 and divide it by 44.0. So 120 divided by 44 gives me 2.727 grams, or excuse me, moles. So that's how we convert grams to moles, in case you're not familiar with that, or in case you just forgotten because it's been so long since you had chemistry. Does everybody follow what I did? I didn't actually show the math there because I ran out of page, out of work on here. But let me do it up here on this part, just to make sure you guys all see it. Okay, so what I'm going to do is I'm going to say N is equal to 120 grams of CO2 divided by 44.0, and actually this is 0.0 there too, grams per mole. And that gave me 2.7272 moles, which is how we got that. Okay. Any questions on that? Okay. So that's how we get the lowercase n. Does anybody know what the uppercase n is? Not the one with the subscript A, just the uppercase n like I drew in the blue above.
The number of molecules?
Exactly. So keep that in mind. Whenever you see just a capital N sitting out there, that's supposed to be the number of molecules. Last time I gave you the various values of R. I will tell you this just to warn you, at least back in the day when I went to school, there was a thermodynamics course that you'd take. I took the physics one, but there's also another one that's for engineers, and it's normally called steam table thermodynamics or thermodynamics for engineers. In that particular course, they use a very different ideal gas law, or very different ideal gas constant. They actually use something like R divided by the molecular weight. So you literally have a different ideal gas constant depending on what gas you're using. So just be prepared. Nora, had you run into that already? I saw you shaking your head. Yeah. So I figured they're probably still doing that. I have some old engineering thermodynamics books that I've worked my way through just when I was transitioning to do engineering work, just because I was interested. And I saw that they were doing that. So I figured they probably still did. All right. Now that I've got that out of the way and you know what to expect, we've got several more minutes. So I'm going to I'm going to follow your book's lead, and your book says in exercise D, return to the chapter opening question on page 492. Try to explain why you may have answered differently the first time. So let's look at page 492 and just see what this thing is talking about. So I'm going to do this in real time on here. I'm going to stop sharing my screen and start sharing a different screen that happens to be my screen. So now I'm going to screen share that one. Okay, so now you see the opening page. By the way, that's Arch. I think that's Arches National Park, or it might be It might be the Windows one, but anyways, it's a park in Utah. I've been there. It's pretty cool. Beautiful place. But anyways, let's look down here at this chapter opening question. A hot air balloon open at one end. See photos above. So there's your hot air balloon. There's another hot air balloon. Notice the big gaping hole in the bottom. That's what they're trying to point out to you. So a hot air balloon opened at one end rises when air inside is heated by a flame. For the following properties, is the air inside the balloon higher, lower, or the same for air outside the balloon? So temperature. Is the temperature of the air inside the balloon higher, lower, or the same as the air outside?
Higher.
It's higher. That's what the flame is used for. Okay. 2, is the pressure inside of the balloon higher, lower, or the same as the pressure on the outside?
Higher.
Yes, I would say it's a little bit higher. That's why the balloon is able to stay taut. And that's also why the air will slowly choose the coldest of air to be at the bottom of the hole where the hole is, and it will actually leak out. And then finally, what about the density of the air inside of the balloon compared to the density of the air outside of the balloon?
Is it less dense?
Yes, it should be less dense as long as it is floating. If it's sinking, then they've either added more weight to the thing that it's trying to hold up, or you've actually gotten the density closer to or even equal to the density of the air. All right.
I was just thinking it would be because the volume is increasing because the balloon is sort of like blowing up.
Right.
Yeah.
Yeah, that's accurate too. So one thing I wanted to point out about that is, let's see. So if you look at the ideal gas law, I'm going to stop sharing and go back to sharing my iPad now. It's not always easy for you to see this, but once you've seen it, it should be pretty straightforward. So I'm going to show it to you real quick. So the ideal gas law, for instance, is P V equals, I know you can't see it yet. I'm just writing it ahead of time. So PV equals nRT. Now N equals the number of moles. And we just figured out that we can find the number of moles in basically by taking the mass. Well, let's do it a different way. Let's take the lowercase mass, which is the mass of the sample, in other words, and divide it by the molecular mass. Okay. So now you can say PV equals the mass divided by the molecular mass times R times T. And from that, you can see that P times big M, the molecular mass, divided by RT is actually equal to M over V. Does anybody know what M over V is?
Density.
Density, exactly. So the density, which is defined to be mass over volume, is actually equal to the pressure times the molecular weight divided by the ideal gas constant times temperature. So from that, you can see that as temperature goes up, the density must go down. That's basically what that exercise was showing us when we were talking about the balloon. Does that make sense to everyone? All right. Now your book has another exercise. I don't remember what exercise I'm on now. I'm going to assume exercise 4, maybe exercise 5. So let's do exercise 5, or example 5. So an ideal gas Now, as the semester goes on, we're going to take the training wheels off. We're going to stop calling things an ideal gas, and we'll just say a substance in its gaseous state, because you'll slowly learn from reading this chapter exactly when gas behaves like an ideal gas. So right now, by us stating an ideal gas, we're taking the rights of you to make that judgment call away, because we're assuming you're a little too new to understand. So that's really why they keep saying that. So an ideal gas is contained in a steel sphere at 20, let's say 29.0 degrees Celsius, and let's say 1.04 atmospheres of pressure. Okay. If no gas is allowed to escape, well, I shouldn't write that there, is allowed to escape, and the temperature is raised to 140 degrees Celsius, what will be the new pressure? Okay. So this is one of those cases where you don't necessarily have to use everything. Notice they didn't give us anything about the mass, right? But it's in a solid or inside of a steel sphere, and no gas is allowed to escape. That means N is one of the constants. And since it's a steel sphere, that means V is a constant. So in our solution to this, we first note that N is equal to a constant and V is equal to a constant. So if we look at the ideal gas law, PV equals nRT, we know that N and R and V are all constants. So I can write nR over V is equal to P over T. So what that means is P1 over T1 is equal to P2 over T2. So that's why I was telling you last time that you don't always have to use the ideal gas law in the form PV equals nRT. You can sometimes just use two of the variables on each side of the equation, like in this case, P over T. So we know that the initial pressure was 1.04 atmospheres. So 1.04. Now, conversion between atmospheres and pascals is just a multiplicative conversion. In other words, I multiply 1.04 atmospheres by 1.013 times 10 to the 5th Pascal divided by 1 atmosphere. And that converts it to pascals. Well, if I did that to this one and I did it to the other one, you could see that that factor of 1.013 times 10 to the 5th Pascal over 1 atmosphere is going to cancel each other out. So I'm actually allowed to use it in atmospheres. Now, the conversion from 29 degrees Celsius to the absolute temperature in Kelvin is an additive conversion. So you can't just do that on both sides and have them cancel out. So you actually physically have to put in a Kelvin temperature. So 273 plus 29 would be 293 plus 9, which would be 303. 302. excuse me. So this would be 302 Kelvin. What we're looking for is P2, and what we know is T2, and T2 is 140 Celsius. But again, I have to use absolute temperature. So that'd be 273 plus 140. That would be 373 plus 40. That would be 413 Kelvin. Okay. I'm going to now check my work because I hate doing addition. It's my least favorite arithmetic operation. So I'm going to do 29 plus 273, and I got 302. That's good. I'm going to do 140 plus 273. I got 413. That's good. Okay. So I'm just double checking. All right. Now all I have to do to solve for P2 is I've got to take 302 Kelvin, divide that by 413. Whoa, no, I got to do the other way around. Nora was just getting ready to catch me. I know she was. Crack, baby. So 413 Kelvin over 302 Kelvin. Notice the Kelvins are just going to cancel out, and that'll be multiplied by 1.04 atmospheres, so that I get P2 is equal to 413 divided by 302 is 1.36. Now I multiply that by 1.04, and I get 1.422. Obviously I had no more than 3 sig figs, so that last digit's not a sig fig, and it comes out in atmospheres. So that's our answer. Any questions on that? No questions? All right. Here's another neat question. What is the volume of 1.00 moles of an ideal gas at 819 Kelvin and 1.00 atm. In other words, the pressure's 1 atmosphere. Anybody think they have any idea how to do that? Remember what I told you about the 22.4 liters? Anyone? Okay, big hint here. 819. Notice that ends in 3, right? And if you multiply 3 times 3, or excuse me, that ends in 9. But if you multiply 3 times 3, you get 9. So guess what 819 is with respect to 273?
$819.
Mm-hmm. It turns out
It's
800
3. It's 3 times 273.
that's the one. Yeah, exactly. So 3 times 273 Kelvin. Now look back at the ideal gas law. We know that PV is equal to nRT, right? And we already know that V, of course, at 1 atmosphere and 273 Kelvin is equal to 22.4 liters. But we also know V is equal to N times R times T over P. So the P hasn't changed, so we don't have to worry about that. But what we see has changed isn't the N, because they said it's 1 mole. It's not the R, because that's a constant. And it's not the P changing, because again, we said it's 1 atmosphere. So what we see's happened is that the temperature actually tripled, didn't it? So now what do you think the volume is?
Triple.
Exactly, which would be 60. It'd be 66, but then you got to do 3 times 4, so that'd be 1.2. So it's 67.2 liters. This is what I meant by telling you that the 22.4 liters is a number that us physicists and us chemists and scientists generally have memorized. And it's not so much that we took time to memorize it. It's more like we just used it so much that it got stuck in our head and it's there. So any questions on that?
So if we're missing information on a problem and we have to use something else to solve it, it's most likely like we need to do some sort of ratio depending on what we're given.
Exactly. That's sort of the trick with the ideal gas law. And it turns out there's other versions that help too. For instance, like when you have an adiabatic reaction going on, then it turns out that P1 V1 raised to the gamma power is equal to P2 times parenthesis V2 close parenthesis raised to the gamma power. So that's another equation you can use in addition to PV over T equals PV over T. But yeah, that's what I'm trying to show you with this is there's a lot of different ways to solve and use the ideal gas law. And it doesn't always just have to use PV equals nRT. In fact, next time I'm going to use kinetic theory, and you can either look at it as I'm using the kinetic theory, which pretends the molecules and atoms are like little billiard balls that collide elastically. In other words, no kinetic energy is lost, and they don't have any forces of attraction between them, which is sort of the definition of what an ideal gas is. So I'm going to pretend like atoms or molecules are made of little pool balls that collide elastically. And from that, you can sort of consider it that I derived the ideal gas law, or you can consider it that I employ that fact with the ideal gas law to find out what the average speed and kinetic energy of the atoms or molecules in that substance are. So it's a lot of cool stuff. Let's do another example. And this one, that was example 6. Sorta. I did one that sort of wasn't really an example, so it should be called sort of 7 if I'd counted that one. So now let's do example 7. So let's imagine that we have a lift bag like we use in diving. We have a circular lift bag like you use in scuba diving. So just for the record, what that is I used to work at a dive shop, and at the dive shop, this is on the Outer Banks, and Virginia is pretty good at this too, but North Carolina, it's called the Graveyard of the Atlantic, and it's called the Graveyard of the Atlantic for good reason. Like I can walk from the beach into the water and swim to 7 different ships just in my part of the beach. That's just from Hatteras up to the Virginia line. So I literally have that many shipwrecks that are swimming distance from the shore. So yeah, we got a buttload of shipwrecks. Well, a friend of ours, when I was working at the dive shop, really loved the tarpon. which was a ship that was sank in about 165 foot of water, and it had a ginormous brass bell on its deck. And they really, really, really wanted to get that brass bell, and it's far enough offshore that it's not considered protected, or at least that's what the laws were when I found out about this. Okay. So they were actually engineers by practice, or one of them was. So he took his 24-foot Albemarle, which is 24 foot is the length of a boat, and it happens to be a pretty nice brand of boat. A 24-foot Albemarle is sort of a workhorse of workboats. But he managed to build a crane type system across the gunnels of this. And we used lift bags, or I say they used lift bags and this crane to lift this brass bell, which literally weighed well over 2,000 pounds. So what they did was they picked up the brass bell by first tying it with ropes and then connecting it to several lift bags. And these lift bags, they're sort of circular, but then they have sort of like a hot air balloon. They're sort of shaped like that. And then they just take their regulator and hold it under it, and it fills it up with air. And air has a density of about 1.29 grams per cubic meter, whereas, 1.29 kilograms per cubic meter, whereas water has a density of about 1,000 kilograms per cubic meter. So you've got a super advantage by using air, and that started to lift it off. And of course, you're in a dangerous spot there, because if you're the scuba diver down at the bottom and this thing starts to go up, what's going to happen is it's going to go up, go up, go up. And the faster it goes, or the more it goes up, the faster it gets, because the actual lift bag is expanding because the pressure's decreasing on the actual bag. So the volume increases according to Boyle's law up until some maximum. But that gets a very high speed. And then as it gets to the top, it'll literally pop out of the water. The lift bag will, at least some fraction of it will pop out of the water. The rope can very well get slack. And then that 2,000-pound bell would fall 165 feet to the ocean floor. And you're probably not fast enough to swim out from under it, and you will, get crushed by it. So this guy that was an engineer was a little smarter than that, and he went ahead and tied a crane to it as well, and then to use the bare minimum amount of air with the airbags to lift it. So you use the air in the airbags to get it lifted a little bit. Then you can run ropes under it carefully without getting your arm caught, because you have a certain amount of time you're allowed at the bottom at 165 feet. And if you stay much longer, you're going to have an appointment with the doctors in Duke. So that's a bit of a problem. So what they did is they used the lift bag to just minimally lift it, and then connect it with the line, the cable, and I think they used the chain actually, the chain to pull it up. And then if the thing fell, either the boat would flip, or the crane or chain system would break, or you'd be safe. So they were betting on it being safe, but they did end up getting it. So it's kind of cool. So what we're going to do is imagine that sort of scenario is we're using a lift bag, and we're going to try to make some predictions about what that lift bag is going to do. So let me turn on my share screen again and do example 7. I think it's going to come on eventually here. It's a really slow process. I'm not sure why it's so slow. Oh, it just completely stopped that time. Let's see if it's going now. Come on, come on, come on. There you go. Okay, so now we've got this. What I'm going to do is I'm going to imagine a lift bag has a 40 centimeter radius. Ah, crap. Keep making the thing erase. I'm going to take a bag and assume it's a perfect sphere, and assume R is equal to 40.0 centimeters. This is not a big lift bag. Some lift bags are like 8 foot across. Most of them are more like a meter or 2 meters across. Okay, so that's at the top of sea level. So the pressure there is 1.00 atmospheres. And now I'm going to bring it down to 99 feet. And I'm going to use 99 feet because I happen to know that when you're down there, the pressure is 2 atmospheres at 30 feet or 33 feet in freshwater, 3 atmospheres at 66 feet, and 4 atmospheres at 99 feet. So the pressure now is 4.0 atmospheres. And I can call that 4.00 really. So let me do that just to keep all our sig figs helpful. Now, what I want to know is what is the radius of the bag now? Okay. So we have here a volume changing and a pressure changing, but we don't have a temperature changing necessarily. Obviously, the water is probably colder at 99 feet than it is at 0 feet. But we're going to pull this bag down really strong, really fast. In fact, we might imagine a blue whale or a whale shark has pulled the bag down. So it's like a, you know, like in Jaws, the movie, when they tied those big floats to Jaws and Jaws just yanked them under the water. There's going to be something that happens quickly like that. So what I'm going to say is the ideal gas law tells us that I can assume P1 V1 is equal to P2 V2. Now, the volume, if we really assume spherical volume, then V1 is going to be 4/3 pi R1 cubed. And then P2 and V2 is going to be, I should put a 1 right there. And I'll put a 2 right here. So now I'm going to say 4/3 pi R2 cubed. You can see from this that the 4/3 pi cancels out. And you can find that R2 is in fact going to be equal to, we'll take P2, or excuse me, P1 over P2 times R1, and that's going to be R1 cubed, but we're going to take the cube root of it. Excuse me. We're going to take the cube root of everything like that. So that should give us the right answer. Does everybody agree with that? And does everybody understand what I did? Anybody have any questions? All right, so I'm going to take the third root of P1, which is 1.00 atmospheres, over P2, which is 4.00 atmospheres, times R1 cubed. So I can actually, since that's cubed and I'm taking the cube root, I can just leave the cube root there and just write R1 next to it. And I'm going to say that's 40.0 centimeters, and life is golden. So really, it's going to be just the cube root of 1/4 times 40. So 0.25 raised to the 0.3333333 power, which is 0.62996. Now I'm going to multiply that by 40. And that gives me 25.20 centimeters. So that's our answer. Okay. Any questions on that?
Can you just keep the the problem here for a second so I can continue copying?
Yeah, no problem.
Professor, what was the problem asking for again?
I just asked for how big the balloon would be when we brought it down to 99
Oh,
feet.
okay. Okay.
That's actually a very, very important question.
Yeah.
Okay, so I think we've done plenty here. I kept you a little late last time. It's now 7:38. Class is supposed to be over at 7:50. I think the other examples in the book more than show you enough. And in fact, the ones I've shown you are somewhat like some of the examples in there, but some of them are just entirely different. And I think if you just look through chapter 17, you'll see plenty of different examples of using the ideal gas law. So you can move along as well. Then they also give you that other version of the ideal gas law with the Boltzmann constant. So I think this is more than enough. Let me see. Maybe let's see if I want to do this one. No, that's not good. No, that's pretty straightforward. I was just looking, your book has an example 1714 where they ask you to use Avogadro's number to determine the mass of a hydrogen atom. So basically what you're going to do is grab the molecular weight, which is supposed to be grams per mole of hydrogen, which happens to be 1.0082, I think, or something like that. If you take that 1.0082 times 10 to the negative third kilograms and divide it by Avogadro's number, which is 6.022 times 10 to the 23rd, you get 1.67 times 10 to the negative 27 kilograms, which is basically just pointing back to how I told you that U is essentially equivalent to 1 over Avogadro's number. So that's an example that I've more or less already worked. There's another one where they want you to estimate the number of molecules you breathe in. If you breathe in a liter of air, that's pretty straightforward. That's another good example. I like a related question that's kind of neat, and I'll tell you about it now. So there's 2 really cool statistical anomalies that occur as a rule of thumb in nature. I'll tell them to you really quickly. So it turns out if you realize that we're just sort of recycling the air from one generation to the next, the total number of air molecules is essentially the same on our planet Earth. And if you see what fraction of the number of molecules is 1 lungful of air, you will ultimately discover that basically you have at least 1, if not several molecules in your lung at any one time that were once in the lungs of, say, George Washington. Kind of gross a little bit thinking about it, but I think it's pretty cool to think about. That's one of the anomalies. Another anomaly is this. Imagine going up to the ocean and you take a single cup, which is 8 ounces, and you pick up a cup of ocean water. Okay. Or you could just fill it up with water from your tap. Either one, doesn't really matter. The main thing is you now take that water and you throw it into the ocean and you come back 20 years later, 40 years later, 80 years later, whatever, just long enough for the ocean to completely mix itself. And you calculate how many atoms in a new cup of water was in the original cup of water too. If you do that statistical analysis, you'll discover that about 100 atoms of that original sample will be in your cup now. Isn't that crazy? So that's just something I find extremely interesting, and kind of cool about the laws of big numbers. But looking at the examples in the book, I don't see any reason to go over anymore. You guys are free to go. I will wait for the last person to leave in case anybody has any questions. But other than that, you're free to go. Remember, we do not have class Monday for Memorial Day. So let's be thankful for those people that died for our country, and enjoy your time, and then come back on Wednesday and we'll jump into chapter 18 and hopefully finish that in one day. I'll email you when your syllabus is up. Have a good one.
Thank you. Have a good one.
You too, Hilram.
Hey, Professor, I had a question about the concept homework.
Yes.
I'm literally stuck on the second question. I don't know if my brain's not working or something, but I can't figure out part C to question number 2.
Do you have it pulled up on your computer screen?
I do. Yeah.
Okay. I'm gonna set it where you're allowed to share, and you
Mm-hmm.
can show it to me so I know what you're talking about.
Okay. All right. Here it is.
Hopefully.
So it had us calculate below what temperature does water shrink when heated, 4 degrees Celsius, and then the 70 degrees Celsius, which lines up with this here, the 600
Mhm.
beta, but I can't figure out like where this came from. I have the answer because I found it, but I
Mhm.
don't know exactly how to get there.
Okay, the relative density of water is determined by
Mm,
the rate at which it expands. I'm trying to read and move this little window out of the way so I can read it. It says the
I
relative
can-
density of water is determined by the rate at which it expands and contracts with changes in temperature. At approximately what other temperature, T, does water have the same density as at 1 degree Celsius? Okay. So immediately what I think of is, if I look at that graph that your
Yeah.
book has, it has a sort of parabolic density curve.
Right.
And you see clearly on each side of 4 degrees Celsius,
Mhm.
you should have equal densities. So 4 degrees Celsius is
Which is like 3.
right, is like 3 to the left
Mm,
of of 1, right? And they said at 1 degree Celsius. So you should go 3 to the right of 4 degrees Celsius to, if that really is a parabola. So you can sort of think of that as 4 plus 3 should give you around 7. And I
Mhm.
suspect that's why they took 8, because they normally allow a error of plus or minus 1.
Oh. Okay, because that would have been my original answer, but I wasn't sure about it. That's why I went to go find what the actual answer was, because I didn't want to keep using attempts.
Right.
But if
The
7 works, then that makes sense.
Yeah, I suspect that 7 will work, and that's the quick and dirty way of doing it, assuming that the symmetry
Yeah.
is there. Now, when I look at this, I'm looking at T equals 0. I assume that's the
Mhm.
other side over there. Oh, and that's beta. Okay. So
Yeah.
since that's beta, remember that's beta, that tells you how the volume changes. So you could also in principle use delta V is equal to V0. Let me
It's like alpha V0 times delta T.
Right, except for instead of alpha, you
It's
can use
beta.
beta.
My bad.
Yeah.
Yeah.
Let me see. I'm gonna try to write that out real quick. So delta V is equal to beta V0 delta T. What you want is delta V to equal negative delta V from 4 to 1. And that's going to be 4 to question mark. That's what I'm thinking. Because obviously when you go from 4 degrees Celsius to the left, the density is going down. Oh, it's got to be plus on both sides. And when you go 4 degrees, from 4 degrees to the right, the density's got to go down as well.
Right.
And the density is inversely proportional to the volume. So
Mhm.
yeah, I'm not seeing a way that jumps out at me with
No.
by calculation.
It's not making sense, but something in my head told me that it was around 7, and I originally thought that it was. I think I was just like doing something with like 70 degrees and thinking like 470, like I don't know. It just didn't make sense at all, like conceptually.
Well, I'm also going to look at, let me see what I have here. I'm looking at the section where it says anomalous behavior of water below 4C.
Mm.
And I'm looking at 1 degree Celsius. It appears probably be 0.999. So I can literally take from the graph and figure 1713 and
Mhm.
get about 7 again that way. So it does look like it's a symmetric graph. It depends on how wonderful that graph is and how accurate it is.
You're
You
saying
can
from like here to here, like that
yes.
symmetry
Oh,
across.
oh no,
okay.
so there it's actually different because they're using beta. But if you look in the textbook
Oh, okay.
on section 17-4-3,
I think it might be here.
it has 2 graphs. You could in principle use those 2, and that might actually be what they're doing.
To like
I'm not
compare.
immediately coming up with a way to use the delta V, but I'll play with it, and if I can figure out one, I'll let you know. I don't
Right.
think that's it. I think they just expect to use the symmetry, but I'll play with it a little bit, and I'll send out either an email or announcement to everyone if I find it.
All right, thank you. That would really help because that caught me off guard. I didn't know what was going on there.
Yeah, that's kind of cool. I like the problem. Now I'm really interested, so I'll see what I can figure out and let you know something.
Okay, thank you.
No problem. Have a good one,
Have a
Nora.
good night. Appreciate it.
You too. How about you, Bohan? You
Professor?
or John have a question? Yes.
Oh, I was just going to ask, so anything we do in lecture, in terms of like the examples and practice problems and things like that, if I ever want to review it, I haven't taken a look at it yet, but is it available on your YouTube or no?
So the YouTube video I usually post within an hour or so after the class. If not, sometimes it might take till the next morning, but the notes are usually within 20 minutes after the class.
Okay.
And they're
Okay, I
posted
just
to
want to
Google
make
Docs.
Okay, got it. Yeah, sorry, our first class, my Zoom kept cutting in and out.
Yeah.
And then my computer was having issues, so I missed bits and pieces here and there. So,
Okay.
but okay, got it. Sounds good. Thank you.
All right. Have a good one, John.
You too. Bye-bye.
What's up, Bohan? Do you have a question?
Hey, Professor Young. Yes, I do have a question, but it's not too much to relate our like, books. It just one of the thing we mentioned earlier about the absolutely 0 273. That thing.
Right.
Yeah, I was just wondering. So is this a number? It's not exist, right? It just kind of like a we're guessing. It's not like it's not like it exists like all the temperatures that we can create, right?
Yeah. What we found out is another version of the second law of thermodynamics. At least I did not read this publication. I've just read this somewhere else that someone has suggested and proven that another version of the second law of thermodynamics is that it's impossible to reach 0 Kelvin, which is negative 273.
Okay.
In fact, the closer you get to it, the more energy it takes to get closer to it. So,
right. So if it really exists in the university somehow, that means you should have 0 kinetic energy, and you should have
right. We know for a fact that part's wrong just because quantum mechanics gives us 0-point energy, which you might have seen in The Incredibles, the movie.
So that's just we're kind of like assuming that there's a low temperature like that. We said that's a 0, but there should be not exist.
Yeah.
Okay.
And actually, just because I think you might be misunderstanding a little bit of what I'm saying. Yes, it does seem to be absolutely false that molecular activity stops at 0 Kelvin, but it also seems that we can't purely get to 0 Kelvin, but we can get as close to it as we want.
Oh, Okay.
That's my understanding of the latest work regarding that second law of thermodynamics. But again, I'm literally going, I can't remember where I read it. I don't remember. So I might be giving you some pseudoscience. I hope I'm not. I will definitely look it up now that I've answered it. But I'll let you know if I find out differently.
Okay. Yeah, I just interesting saying that. I was wondering because I saw this number a long time ago in the chemistry class, like it counts absolutely zeros. And then just a couple of weeks ago, I read from somewhere the news said if it's really like if that really happens with the absolute zeros, they said that the light should be stopped. Like even
Oh yeah, absolutely. It would definitely be an end of life for everything.
yeah, they said the light, so the like the light speed. They said it will even frozen the light. So that's why I was just kind of thinking about it. It's kind of interesting. So,
No problem.
thank you.
Yeah, have a good weekend, Bohan.
Yeah, you too. Have a wonderful holiday with your family.
Thank you. Have a good one. Bye-bye.
Bye bye.